Hello everyone. In this video, we talk about finding loss functions for regression problems. Loss functions are crucial in machine learning because they measure how well a model's predictions align with the actual outcomes. By quantifying the difference between predicted and true values, loss functions guide the training process, allowing algorithms to adjust model parameters to minimize errors. To put this in a simple context, recall this diagram that we have for a general machine learning algorithm. We typically start with the input features. We go through some data transformation to get some predicted outputs. So you can think of these as a function of input features. On the other hand, we do have access to expected or true outputs. And therefore, in this stage, which is the main focus of this lecture, we want to measure the difference between predicted and expected outputs. And this loss function, once we find it, now we can minimize it to minimize the disagreement between the model and the true outputs to find the optimal values for the weights or parameters of our model. Again, I want to emphasize that the main focus here is on the loss or cost function, but nevertheless, it's important to put this into the full picture. So that's why we will talk about three parts of this diagram that we have here. A simple case of data transformation, driving the loss function for regression problems, and then eventually we're going to see that how we can solve this optimization problem in this simple case. And therefore, what we learned from this lecture, it's very important for later topics that we are going to cover because it's the building block for more advanced machine learning algorithms. If you recall, we show a data set or represent a data set using these input-output pairs. And the small n here is the index for the sample. So n, for example, 1 means sample number 1, n equals 2 means sample number 2. And we do assume that we have this uppercase or capital N as the total number of samples or observations in our data set. Now, in this case, we assume that each output is continuous because it's a regression problem. And also it's a scalar or single number to make things simpler. But these input features or xn's are in general vectors. For example, it can be information about income, debt, and other information about borrowers in the bank loan default problem that we have. Therefore, now we need two sets of indices to represent each element of xn. Because xn is a vector that has d elements, now we can use a second index, 1, 2, up to d, to show that these are the d elements that are included inside this vector. However, in this case, I like to drop this first index n and just simply refer to these elements of xn by x1, x2 to xd. And this is just to make sure that the notation is easier to follow. But if you really want, from now on, whenever we are, for example, saying x1, you can use xn1. But it is kind of obvious that we are focusing on one sample, so we don't have to explicitly use this index n. With this in mind, let's look at the first part where we want to do data transformation. And we're going to focus on a very simple case known as linear regression, where you assume that this function that transforms the input vector x is a weighted sum or linear combination of the inputs. This means that you usually have a bias or intercept term, and then for each input feature, you have a corresponding weight or coefficient, and we do this multiplication and add all these multiplications together. So for now, let's say that we have this W0, and we just keep that. And for the rest of these terms that we have here, we can actually write this in a compact form. And this is something very important in machine learning, because we don't want to work with summations and for loops. We want to write things in very compact form. Typically, this means that in the form of vectors and matrices, etc. So one thing that we can do, we can define a vector W, which contains W1, W2 to WD. And if W is a column vector, the transpose now would be a row vector. So it's of size 1 by D. And then X has the elements, as we just saw here. And now if we find we do this multiplication, the result is 1 by 1, which means that it's a scalar, and it's the sum of the products, meaning that W1 times X1 plus W2 times X2 up to WD times XD. And we can also write this as, you can see here, as simply the dot product or inner product between W and X. And by definition, this is equal to W transpose X when you assume that W and X are both column vectors. And the other thing also we can do to make this even like in a better representation, you can absorb this W0 into this weight vector that we had W1 and WD. And the trick is that now we also have to augment this input vector X, and we can simply do this by adding the first feature to be just simply 1. And this works because now if I find the dot product or inner product between these two augmented vectors, that now they have D plus 1 elements, now we can see that we have W0 times 1, which is W0, exactly what we wanted here. So you can assume that this is actually W0 X0, where X0 is always equal to 1, and the rest is exactly the same as before. Therefore, the main assumption for data transformation when you're using linear regression is that the input gets into this dot product or inner product with these D plus 1 weights or parameters, and the result is your predicted output. So now the question is, what is a good loss function? Meaning that in this case, now we understand how we are going to transform the inputs, but how do we have to measure the difference between predicted and expected outputs? Since we are working with regression problems and continuous outputs, a very intuitive way of defining loss or cost function is to simply subtract these two values and raise them to the power of 2 to make sure that they are all non-negative, so errors do not cancel each other. It's obviously a problem if some errors are negative and some are positive, then they can cancel each other and you get 0 error when there is actually a lot of error in your system. So that's not a good idea. But as long as you make sure that you take for example, like raise to the power of 2 or take the absolute value, then that seems to be a very valid choice. But, can we prove, statistically speaking, what is a optimal loss or cost function? And in order to answer this question, we're going to use the principles of maximum likelihood estimation that we discussed in the first lecture. So in order to use maximum likelihood estimation, we need to have some distributional assumptions. So we assume that the output of our regression model follows a normal distribution, and the normal distribution needs two important pieces of information: the center or mean and the variance. And we assume that the center is actually this function, which is the dot product between X and W. And we assume that the variance is fixed. So this is a very big assumption here because we are assuming that the variance is independent of the input, independent of the weight vector. And although this is sometimes true in practice, but in many cases, the variance, for example, depends on the magnitude of the input. So in that case, obviously what we are driving here is not the optimal choice. And we're going to talk about that later on in terms of more advanced machine learning methods. But for now, we make this simplification here to assume that the variance is fixed. And you're going to see why this is very helpful to simplify the derivation of the loss function. So just to write this down mathematically, we assume that the output given the input and weight vector follows a normal distribution with this mean and this variance. And if we remember the PDF of the normal distribution, you know that this is 1 over square root of 2 pi sigma squared times exponential of minus 1 over 2 sigma squared. And then we have y minus f of x and w squared. So that's the PDF with variance sigma squared and mean f of x and w. Now, the next thing that we want to do is we want to use maximum likelihood estimation. And as I mentioned before, this is equivalent to negative log likelihood function that we want to minimize. Because the reason that we want to minimize this is because we add this negative sign. So we convert the maximization problem to a minimization problem. This is the common approach in machine learning. And this is what we derived in lecture 1. So the negative log likelihood function is negative sum of log of these individual probabilities that we found. And since this probability that we have here has two terms, is a times b, we can write this as log of a times b, which is log of a plus log of b. So you can see that we can simplify this, given that these are all linear operators. We can write this as negative sum of log of a and negative sum of log of b. And then we can substitute in these values for a and b. So you can see that in this case, they get negative sum of log of this a, which is 2 pi sigma squared raised to the power of negative 1 over 2. And then the second term, which is the negative sum of, in this case, we have log of exponential. And remember that the logarithmic function and exponential function are inverse of each other, meaning that they cancel each other. So we get what's inside this exponential, which is negative 1 over 2 sigma squared yn minus f of xn and w. And here we want to make sure that we put that index n, which is the sample index, because now we have this summation over all the data points for all the samples. So that's something important to remember since we removed that earlier on. And if you simplify this first term, you can see that since the term here does not have any index n, this is n times what we have here, and which is n over 2 log of 2 pi sigma squared. And this negative and negative sign, they cancel. So you get 1 over 2 sigma squared, this summation of the differences between true and predicted values. And here is why that constant or fixed variance really matters. Because now, if you want to minimize this term doesn't have any dependence on W. And the same thing here, this does not have any dependence on W. And what this means is that if you want to minimize this, and in fact, we really don't want to just minimize, we're looking at the minimizer, meaning that what value of W minimizes this whole term, then we can easily remove this first term because it does not have any dependence on W. So you can think of this just as a constant where you're adding, like, let's say 2, 3, or some fixed number to a loss function, and that does not change the minimizer, right? It will change the minimum value, but it does not change the minimizer. So all in all, what this means is that the loss function that we have, the main part is this summation, which is the sum from 1 to n, yn minus f of xn and w. And we can choose any constant as long as it's a positive constant here. It is common to keep this 1 over 2, and we're going to see later on that this really helps in terms of being able to solve this problem, in a sense that makes the formula a little bit nicer because you have some extra factors of 2 that this 1 over 2 will cancel them. But this is obviously optional. In fact, if you're looking at something known as mean squared error, which is very similar to these, the difference is that instead of 2, you place the uppercase n here, which is this average of the square differences between true and predicted values. So this constant here does not really change the problem again because we are looking at the minimizer of this function. And this function stands for residual sum of the squares, RSS. So you can see that this is what we have actually here in the lecture, that this RSS is 1 over 2, the sum of the differences between true and predicted values. But something, again, that is very important in machine learning, we do not want to work with summations, for loops, etc. We want to write these things in compact forms using vectors and matrices. That's the key idea here, the key idea behind neural networks and deep learning as well. So how can we do this? So it's relatively straightforward in this case. You can place all the output values that you have in a vector y, so it has n elements, n by 1. You can also place all these input features that you have in a matrix. So the way that we do this is that we put each input feature vector as the row of this matrix X. So if we assume that X1 to Xn are column vectors, we're going to do the the transpose to make sure that now they're row vectors. And now we can stack them together in this form so that we get n rows. So each row corresponds to one sample or observation. And then each column corresponds to one feature in your data set. And since we augmented the data set that we have with that extra feature, which is always 1, now you see that we have d plus 1 columns. But we have to remember that given the way that we augment these input features by adding that element 1 or x0 equals 1, the first column that we have here includes all ones. And then the rest of these columns are actual feature values that we have. And then the weight or parameter vector that we have, this W, also contains d plus 1 elements. And interestingly, if we multiply this x by w, so this is a matrix vector multiplication, you can see that we get the multiplication of this first vector or first row vector by this column vector, which is equivalent to the dot product or inner product between x1 and w. The same thing for the second element when we do this multiplication is the dot product or inner product between x2 and w, and then xn and w. Therefore, if we do this matrix vector multiplication, we get all these predicted outcomes or predicted outputs in one operation. And then the nice thing is that if you're looking for the differences between true and predicted outcomes, we can simply subtract these two vectors. So now we do this element-wise, meaning that the first element is y1 minus the dot product between x1 and w, and so on. And we are familiar with something known as the Euclidean norm or vector norm here, which is simply the sum of the square of the elements. And that's exactly what we have when we have this RSS or residual sum of the squares, except this 1 over 2. So this 1 over 2 is something that you can add here to show that this residual sum of the squares is 1 over 2, and then the Euclidean norm of y minus xw squared. And this is something that you need when you want to implement linear regression or other machine learning models using the popular scikit-learn package, which is used for machine learning. We always assume that the input metrics or the data metrics is 2D, right? Because we need to have rows and columns. Each row corresponds to one sample. Each column corresponds to one feature, right? And that's clear by this n by d. And overall, later on, you see that in many cases, we do not really call this d plus 1 because these machine learning libraries, they automatically add that column feature, which includes all ones. So in practice, we only have to provide an n by d vector where each row is one sample, each column is a feature. And then everything else will be taken care of in the background. So once we do these, again, the ultimate goal here is to find these weights or parameters. That's what really, learning in this specific problem means that what weights or parameters we have to use to transform the data using this simple dot product or inner product. And we can do this using this argmin. So we want to find the minimizer of this. And Again, the minimization problem is with respect to W. So here is where I would like again to emphasize that this RSS loss function is derived under the assumption of homoscedastic noise, meaning that the noise is uniform across the input space. And this is a very big assumption, and in many cases we have heterostochastic noise, meaning that the noise is input dependent, and therefore this loss function may not give you a good solution or prediction model in general, and that's something that we have to take care of. But for now, let's focus on solving this simplified case that we have. So the idea is that, well, now we have these multiple values of W that we have to optimize. And this means that now we have to extend the notion of derivatives to handle functions that they accept multiple inputs or vector argument functions. And in this discussion here, I'm using n to denote the number of inputs to this function f. This is just a mathematical discussion. So this n does not refer to the sample index that we had before. So this is just simply telling you that if you have a function with n inputs. So do not use this n in the context of the notation that we had before. And this is just a general discussion. So in this case, if you have a function which has n inputs, the gradient is a vector that has n elements, and each element is partial derivative with respect to one of the elements. So if you have, like, let's say a vector x, which has n elements, and you have a function that is the Euclidean norm square of this vector, then we can try to find the gradient. And the idea is very simple in this case. What we do, we can represent what this function is simply sum of the square of the elements. And if you want to find the partial derivative with respect to x1 is variable, everything else is fixed or constant. So the only thing that you have to take care of is this x1 squared, and the derivative is 2x1. The same thing happens when you want to find the partial derivative with respect to x2, with respect to x3, with respect to xn. So you end up with a vector which contains 2x1, 2x2, 2xn. And this looks very familiar because this is simply 2 times the input vector x. And this is a very important thing. So about understanding gradients, because they work with any dimension or any size of input in this case. Meaning that if you have any vector x, and this vector x may have 2 elements, it may have 1 million elements. And if you want to know what the gradient of the norm of this vector is, it's 2 times that vector. It's very simple, right? So it works with any dimension and any vector x. And the same thing happens. So for finding the gradient of the loss function that we just derived, because that's what we should do, right? We need to find the gradient or derivative and then set equal to 0. That's like the first principles of optimization, right? We're using for example, the first derivative test that we know from calculus. So we need to be able to find the gradient of that residual sum of the squares. And in order to do this, we need to know 2 main identities. The first one is that the gradient of the inner product between A and X, which is technically A transpose X, where A is fixed and X is what we want to take the gradient with respect to, we need to find this formula. And again, I think the easiest way to solve these problems is either to look up this information online or through some textbooks, or you can look at some simplified case by expanding these terms. So the inner product between A and X is this weighted sum. And if you take the partial derivative with respect to x1, you get a1. With respect to x2, you get a2. And with respect to xn, you get an. So it's very easy to show that the gradient of A transpose X, or the inner product or dot product between A and X with respect to X, is just A, right? So it's a very simple formula. And we can extend this also to, somewhat more complex functions of X. And in this case, if we have X transpose, remember, X is what we want to find the gradient with respect to. X transpose AX, where A here is now a matrix, right? So if X is n by 1, that was the size that we assumed, then this A is an n by n matrix. Then the gradient, you can do the math similar to what we did, and you can show that it's A plus A transpose X. And because in many cases, this A is a symmetric matrix, meaning that A transpose is equal to A, you can actually show that this simplifies to 2 times A times X. So although this function looks a little bit obviously more complicated than the other ones, but you can see the gradient with respect to X is 2 times A times X. With this information that we have, now we can find the gradient of RSS, or residual sum of the squares. Okay, so let's go through this step by step. We start by writing what this RSS is 1 over 2, and then the norm, the norm, Euclidean norm square of y minus xw. Similar to any kind of norm, we can also write this as xw minus y, so it doesn't matter which one comes first, since the result is always non-negative. And now if you look at the definition of the Euclidean norm square, that's this vector transpose times itself. And similarly, now we can do this transpose here. We get W transpose X transpose minus Y transpose times XW minus Y. And so we have two terms here. We can multiply these two terms, and we end up with 4 terms. So we get 1 over 2, and we get W transpose X transpose XW, W transpose X transpose Y, and so on. So you get 4 terms. So now the goal is to use those identities that we had for gradients to be able to find the gradient of this term, where we broke this down to simpler terms. This first term is very obvious because it's W transpose W, and then there is something in the middle, which you can think of this as that matrix A, and you want to find the gradient with respect to W. So let's look at this. So this is exactly what we have in the middle, and then you have this X and X transpose. So let's go back. You can see that we have W and W transpose, and we have something in the middle, which is equivalent to that A matrix. And this X transpose X is actually fixed because remember, these are the inputs that are given to us. There's nothing to optimize here. What we want to optimize is W. And we can do the same thing for these 2 terms in the middle that we have. So it is kind of, obvious that if we put this W by itself, then everything else that we have here is the dot product or inner product between W and X transpose Y. Something that may not be immediately obvious is that this second term that we have here in the middle is also this dot product or inner product. But to just show you this, we just said that we have the dot product or inner product between W and X transpose Y. So we can always write this as the transpose of one of these two times the other one. And this gives you Y transpose X times W. And you can see that that's exactly what we have here. So overall, this term that we have can be written as W transpose X W minus 2, and then the dot product or inner product between X transpose Y and W, plus this Y transpose Y. And once you want to find the gradient of this term here, so now we can find the gradient of the individual terms and then add them together because derivative or gradient is a linear operator. You can see that this term, Y transpose Y, does not have any W in it because we are taking the gradient with respect to W, so this term will vanish. And then for the first term, this X transpose X in the middle is kind of like that matrix A and is also symmetric. We can easily show this because if you take the transpose of this, it's the same as itself. And you get 2 X transpose X W, so 2A times the vector, and minus for 2. And here you get this vector, which we called before A, as the result, right? So we know that if we have dot product between A and W, and we take the gradient with respect to W, the result would be A, and that's what we have here. And here you can see that why that 1 over 2 really matters, because now we can get rid of these extra 2's. And so this is the gradient of your loss function. And that's what we really need in machine learning to solve optimization problems. And in this simple case, because this is a very simple, data transformation where you find just the dot product and then you have this really nice loss function, you can actually, explicitly solve this problem or analytically solve this problem by setting this equal to 0, right? So we have all this analysis here, and if we set this equal to 0, this gradient equal to 0, you can see that we get x transpose xw equals x transpose y. And I'd like to emphasize again that these x and w are fixed. The only thing that is variable here is this w. And you can analytically solve this problem by finding the inverse of this x transpose x. And in fact, this term that we have here, x transpose x inverse x transpose, is what is known as the left pseudo-inverse of a non-square matrix, right? Because remember, x is this data matrix of size n by d, or the d plus 1. Since it's not a square, we cannot find the inverse of that matrix, but we can find the pseudo-inverse. And that's what is known as the left pseudo-inverse. And so in this case, solving this optimization problem is very straightforward theoretically. However, there are some practical considerations. And that includes the fact that in many cases, we do not want to find the inverse of this matrix x transpose x because of numerical results. For example, it might be ill condition or singular. So you know that in this case, you may get into numerical stability problems. Second, it's very computationally expensive if we have a lot of features. So let's say if hypothetically we have 1,000 or 1 million features, then this will take a really long time to find the inverse of this matrix. In fact, the cost of this inversion is order of d cubed, where d is the number of features. And so if you double the number of features, means that now you have to wait 8 times longer. That's the meaning behind this complexity analysis here. And also in many real-world problems, when you think about modern machine learning, your data set might be too large. You may want to do something with, let's say, a few million samples. And in that case, you may not even be able to store this entire matrix X in the main memory or RAM of your machine. And so that's something to keep in mind, that you may be able to access these data set in batches or in chunks, right? And like having access to the entire thing. So these are the things that we're gonna cover in the next lecture. So that'll become like the motivation behind what we cover next time. But for now, we wanna assume that we can analytically solve this problem when we do have a small scale to medium scale problems. And in particular, we wanna use our first class of linear regression from scikit-learn, which is the most popular machine learning library. And I always recommend you to look at, the documentation page, because that's where you get a lot of information. For example, you know that now linear regression is a class. We define what class means using object-oriented programming principles. We also know that linear regression is part of scikit-learn's linear model module, right? Remember the dot notation that we talk about hierarchy. So there's scikit-learn, which is called sklearn. Then inside that, there is a module called linear model. And inside that, there is linear regression. So here you get some description. You see usually like something called parameters to tell you what parameters you get for this function. When we talk about object-oriented programming classes and objects, remember we have data and functions that are encapsulated. The data or properties are called attributes. This is where you can, for example, find all those coefficients that we had, the intercept term that we had, some other information, for example, whether we want to have access to singular values of the metrics, input matrix X. This is something obviously we don't need immediately, but in many cases, we want to do some diagnostic analysis. We might want to look at those things. The nice thing is that there are some examples always to see how that linear regression class works. Then the methods or functions, because we need a fit function or method to be able to fit the model, meaning that solve that empirical risk minimization problem. Sometimes we want to make predictions. So you can see that we have all these methods that are built in. So that's why it's very important to be able to use these built-in machine learning methods, because they are really written in a way that very accessible. They get a lot of information, although in this case, we can write our own linear regression model, but in many cases that can take a lot of time. So these libraries are really, really helpful. So you can see that you get tons of information here, and that should be your go-to place when you want to start using these methods. But we do include some of this information in these lectures. Okay, so let's start with a real-world example now. So we're going to start working with NumPy and import it as NP because we want to work with numbers. Since we want to import some data that is in a CSV format, comma separated value, and we want to look at this as more like an Excel or a spreadsheet format, we're going to import pandas as PD, and we're going to import matplotlib for visualization purposes. So these pandas has a method called read CSV. So it means that we want to read the CSV file, and you can do this either locally or you can just provide a link for where this CSV file is. Here we provide this address. And once I run this and I use df.head, so this will show me, I believe, the first 5 lines of this data frame. That is true, so 0 to 4. So you see what we have in this data frame. We have information about countries, GDP, and life satisfaction. So what this really means here means that we want to have a machine learning system that if you provide a new country with a given GDP, right, gross domestic product, then we are able to find or predict the life satisfaction score, right? So it is kind of expected that richer countries, people are happier, but we don't know for sure, or we don't know how this thing is related. So we want to do some regression analysis to find this out. The first thing that we want to do for our machine learning model is that the input is, in the simplest case, is just the GDP, right? That would be our input features. Although we can add the name of the country, but since that's text, we cannot really directly add this to our machine learning model. So you can always think about innovative ways to do that. But for now, we just look at this GDP. And you can actually convert this to a NumPy array using the toNumPy method. And the same thing, now you need to have a vector of outputs, or these desired values that we have, and that's the life satisfaction. Something I always recommend you to do, to look at, since you have now NumPy arrays, to look at these attributes shape to see first how many samples you have. So you have 27 samples. And then the other thing that you see here immediately is that for this X, which is the input metrics or the data metrics, it says 27 comma nothing. So what this means is that the way that right now NumPy is looking at this X is that this is a 1D array, meaning that you have only one axis. However, if you look at, for example, linear regression, and let's just, look into the future a little bit and look at what this fit method expects, it says that this X should be a 2D array of size number of samples, which is what we have, 27, by the number of features. So meaning that the number of features, even if it's 1, it should be here exactly 1. And if not, you will get an error message, right? Because the way that this, almost all these fit methods are written in scikit-learn and many other libraries, is that they're expected to be 2D, because we want to have one axis for the number of samples, the other axis for the number of features, right? So you can do this very easily, for example, by saying that we want to reshape this by -1 and 1. So what this means is that, I want to make sure I have one column for that one feature, but I want to let NumPy figure out how many rows I should have. So you can here use like 27 if you want, because we know, but since we want to maybe use with different number of samples, This really helps to make this more generalizable, right? So you can see that now here we have a 2D array because we have two sets of these brackets, but it's exactly the same thing. If you look at it, we didn't change the values. We just made sure that we have two axes because that's what we need to have. But since first we want to write our own linear regression model, we can focus on adding that column feature where everything in that column feature is equal to 1 ourselves. So we define a function at column. You get this input matrix X, and we're going to use np.concatenate to add a column vector of all ones to X. And in order to do this, we use np.ones. We make sure that we have the right number of rows and we have one column. And we are going to put this next to the column vector that now we have for these input features that are here. So let me just make sure that I put these -1 and 1. So we have this information, and we're going to add a column of all ones right next to this. So that's what exactly we are doing here. And once I define this function, I'm going to call this and pass X, and I call this xcon for concatenated. And you can see that now it's 27 by 2. And you can actually even look what's inside it. So this confirms that, yes, we have this column of all ones for that x0, and these are the actual input features that we have. And now in order to solve this problem that we had, since this is a least square problem, so we can call this x transpose x as A and x transpose y as B, and the goal is to find W. And in fact, we can use from NumPy's linear algebra module, linalg, this thing which is called least squares, and you just have to provide A and B. So remember, A is x transpose times X, B is x transpose times Y. That's the nice thing about Python and NumPy and these libraries. It's very easy to read code. And there's this also option here for conditioning if you want to get rid of some of the singular values that are too small for numerical stability problems. But again, this is not a numerical analysis course. We are not focusing too much on that right now, but we just want to show that, well, you can use this least square problem and provide this A and B and solve this problem. And you can see that here, this theta, which is this, the weights or parameters that we are looking for, have these two values. So it's a two-dimensional vector because remember here we have two features, including these constants that we added here. And the other thing is that I'm calling W as theta. I do this intentionally because it is very important when you look at different textbooks, different literature, different papers. We use different names for different variables, but again, this theta is just a name. You can call this W if you want, but that shows that these are the weights or coefficients for the regression problem that we have. And once we find these optimal values of theta for our model, it's very easy to make predictions because remember, the way that we can find predictions in our model is simply by multiplying X by this W or theta. And that's exactly what our prediction model is. So what we do here, in order to plot this in a very nice way, we're going to make some adjustments such as font size, figure size. You can obviously, once you start experimenting with the code to change these things. We use scatter plot to have these 2D coordinates for X and Y values, because here we have a simple problem where we have only one input features. And then we provide our test data, which we assume that we have two values. Since we want to draw a line, you only need 2 points on that line, so you don't need many of them. You can obviously add multiple points between these two values, but for now we assume we have 2 points. And then you pass this into this function that we just defined, and then plot the result using this red dashed line. That's what this means, and it's always a good idea to add labels, so when we plot, we know what exactly we have. So these blue dots you see here, they come from this scatter plot where we have the plots of inputs and outputs. And this red dashed line, or it's basically our prediction model, where we provided the first point and then the end point and then automatically you just connect them. So in this case, we don't need more points, but if this was a nonlinear function, obviously you have to provide more points and then connect them together. And this shows that overall, this is a good model. I mean, obviously, we can say that, well, the variance is not necessarily uniform across the space, that sigma squared that we had. But you can see that overall, this gives us a relatively good result. And do not forget to add labels for your x-axis and y-axis. So now anyone can look at this and say that, well, this is GDP, this is life satisfaction, and this is how these two things are connected. But now let's look at the way that we can use this linear regression class from scikit-learn. So the very first thing is to import this. And in order to import this, we are going to use this scikit-learn.linear model module. So you can see a lot of linear problems are inside this scikit-learn.linear model. And then we're gonna instantiate this class to create this object, this reg or reg. And now that you have this object, now you can call this method fit, where you have to pass your input metrics and your output, because we need both to solve the problem. And again, I emphasize that this X should be a 2D array. And remember, I'm not adding the concatenated metrics here. This is the raw input metrics that I have. So this X dot reshape -1 and 1 is just has one column, which are the actual GDP values in them. And scikit-learn and linear regression will automatically add that column of ones in the background. And now we can look at, once we run this fit method, we can look at the intercept and coefficient values. And if you look at this, this is very much similar to the version that we solve ourselves. So this is a simple problem. You should be able to reproduce the results. The last thing I want to talk about here, one issue that we have is that you can see, for example, here, that the coefficient is really, really small compared to intercept. And the reason is that this coefficient will be multiplied by the feature values, and the features are large, right? Because the GDP values in the given format, they are in, for example, 25,000 to 60,000, right? So this may not be the best option to use because, one feature has to be really, really small and can cause numerical stability problems and so on. So it is very common to do pre-processing. So inside scikit-learn, there's a pre-processing module, and one of those classes is this min-max scaler. As this name suggests, min-max scaler makes sure that all the features are between minimum and maximum values that are provided. And by default, if you look at the documentation page here, and I strongly encourage you to do that, you see that this will map these features to the interval 0 to 1. So if that's what you want to do, you don't have to provide any more input arguments here. But if you want to map to another interval, then you have to provide the min and max values. And then use this fit transform. And now you provide this x min max to your problem. And you can see that now we get a different value for coefficient, which is kind of like in the same order as the intercept. And if we run this, you can see that we get exactly the same model, except the fact that now on the x-axis, we have everything from 0 to 1. So that might be a little bit easier to understand because we have kind of like the mean and max values. And it doesn't matter what exactly these values are, but we know that 0 is kind of like the smallest GDP, 1 is the maximum GDP. I hope you found this video helpful.